So when we're talking about gases, we're basically talking about obviously the state of matter where pretty much everybody has broken apart from one another. They're free from each other. They're flying around. So obviously in that gas state, we have all these gas molecules free flying around. And obviously as they're flying around, there's a lot of collisions that are happening. As we have those collisions with the container, and certain aspects with themselves as well. It creates what we basically refer to as pressure and creates the pressure that we associate with gases. Um, it's obviously the state of matter where it takes a lot of energy to completely get everybody away from each other. Remember, in the solid state, everybody's still pretty close to each other. In the liquid state, still close to each other, but a little bit more room for movement. And really, when we get to that gas state, we have completely basically broken apart everybody away from each other. And when we talk about gases, we oftentimes talk about three really main properties of gases, and that's pressure, that's volume, and that's temperature. So these are the three sort of main sort of values, if you will, or variables that we deal with when we're dealing with gases and gas laws and those type of things. Um, gases completely mix with other gases. And again, that's just a product of them flying around. So obviously, as all these gas molecules are flying around, they are constantly mixing with each other. So they're very soluble with each other. They create a homogeneous mixture, which means everything is the same throughout. Um, gases exert pressure on the surroundings, as I mentioned before. Again, as they're bouncing around, they're usually in some type of container. And obviously, as they hit that container, as they keep kind of banging the walls of the container, they're creating a lot of pressure associated with it. So let's talk about some important units of pressure. Pressure is basically force over area. And with gases, there's a few different types of units that we very commonly come across. And some you'll see a lot, some you might not see so much in chemistry and stuff like that. But the SI unit for pressure is a Pascal, and sometimes even a kilopascal is a common unit of pressure. And that's just the kilo sort of prefix, if you will, 1,000. Um, one standard atmosphere, or ATM, basically, which is a very common unit of pressure, equals 101,325 pascals, or basically 101.3 kilopascals. But really, when we kind of deal with pressure, these are sort of our three main units that we really will see a lot. And that's an atmosphere, which is abbreviated in ATM. We also will see mmHg. MM is millimeters, Hg is mercury, so that's millimeters of mercury. We also see TORR, which is a torr. It's also a very common unit of pressure. One relationship which is important is that a millimeter of mercury is basically a one-to-one relationship with a torr. So it's basically a one-to-one relationship. And basically 1 atmosphere equals 760 torr and equals 760 millimeters of mercury. So this sort of 760 number is a really important number. It's really kind of your conversion factor to go from these kind of basic units. So if you have atmospheres and you want millimeters of mercury or torr, you basically multiply by 760. And that will give you, again, torr are really millimeters of mercury because it's a one-to-one conversion. And vice versa, if you have either torr or millimeters of mercury, you would divide by 760 to get to atmospheres. And again, that'll get you to atmospheres. So that 760 number is really an important number, especially for conversions and doing a lot of gas problems. Sometimes we do need these units in certain specific units in order for everything to work out correctly and everything to cancel correctly. And so you want to make sure you know how to obviously do these conversions. Also, an atmosphere is equal to 14.7 psi, right? Pounds per square inch, like when you fill up your tires, your car or bicycles or those type of things, right? So that's basically pounds per square inch. is 14.7 equals 1 atmosphere. Like I said, pretty much these three that are in the box are really the three that you see the most. There are definitely other units of pressure. For example, another unit of pressure is what's known as a bar, is another unit of pressure, and that's about 1.01 atmosphere. So it's very close to each other. But those three there, like I said, in that box, you definitely need to know these sort of conversions. Definitely the 760 conversion there. And again, a millimeter of mercury is basically the same thing as a torr. So it's a one-to-one relationship, a one-to-one conversion. Any questions on that there? Now, pressure is affected by atmosphere. Whoops, get back here. So obviously, as we go up in terms of above sea level, the pressure gets less than 1 atmosphere, right? That's why they pressurize airplanes when we go up. Also, as we go below sea level, the pressure gets more than 1 atmosphere. Again, why you can't go too deep, just kind of free diving, right? If you go really deep, that's not so good. There's a lot of pressure on your body and stuff like that. So right at sea level, we're at 1 atmosphere. Also, we don't talk too much about it in this class, but in 1A you talk about it. But obviously, as you go up and down, pressure is affected by the difference between sea level, and it can affect things like boiling points and stuff like that, where say something like water would boil and stuff like that by changing the pressure. So the pressure of a gas is measured to be 2.5. This pressure in torr and pascals. So again, we could use our conversions that we saw there. We could start with our 2.5 atmospheres. Again, using our 760 torr is 1 atmosphere as a conversion factor. Again, our atmospheres will basically cancel each other out, and we will convert it into the units of torr, which is what we're looking for. Again, in terms of sig figs, we're really not going to look at this number here. So we would go back to this number here, which is 2 sig figs, and we end up with 2 sig figs on our answer as well. And again, that's a very common conversion that you do, also more common going from torr back to atmospheres. Again, probably not so much pascals happening in a lot of calculations you do, but again, here is the conversion factor. That 101,000 pascals basically is 1 atmosphere. Again, here our atmospheres are going to cancel. And again, in terms of sig figs, 2 sig figs here, really a conversion factor here, so we don't have to worry about it. So we do end up with 2 significant figures there on the conversion. All right, so why don't you take a second here, what is the pressure in atmospheres, and do that conversion. Okay, so looking at this again, it's basically that very common one, that 1 atmosphere equals 760 torr, and that equals 760 millimeters of mercury. So really we could use that as our conversion. So we're starting with torr. We want to get rid of torr, so we will put this 760 on the bottom. Basically, we're going to divide by it, and that will leave us with atmospheres up on top there. And looks like we do get something like 0.863 atmospheres. Again, in terms of sig figs, original number there had 3. Answer here also has 3. So it looks like B is our answer. Any questions on that there? And that is a very common conversion that you do a lot, that kind of dividing by 760 to get things into atmospheres. Again, as we'll see, there's certain gas laws, for example, that you need to make sure everybody's in the sort of atmosphere unit. All right, so which one is the bigger unit here? It would be atmospheres, because in one atmosphere there's 760 torrs, which means atmospheres is larger. And one atmosphere there's 101,000 pascals, which means that's a lot more needed to get the one of those. And one atmosphere is also 760 millimeters of mercury. So our atmospheres here would be the bigger unit of all of them, as one of those represents a bunch of all the other ones. So that means that's obviously a larger value than that. By alternate to that, the smallest unit would then be our pascals again, because in one atmosphere, there's the 760 torr, the 760 millimeters of mercury, and 101,000 pascals, which means you need a lot more pascals to equal basically one atmosphere. And that would make it the much smaller sort of unit. All right, so how do we measure pressure? We measure pressure really with a couple of different devices, but one very common device is a barometer, and that's what a classic barometer looks like. They don't really look too much like that anymore in labs, especially at schools. They've taken a lot of these out because they actually do contain mercury, and replaced it with other types of barometers. In fact, we have digital ones as well, but basic barometers, basically this setup, you basically got a pool of mercury. You have this sort of glass column here, and it's basically open at one end, closed at the other end. And basically, as the atmospheric pressure basically exerts there on the mercury, and basically the mercury will rise or go lower in the tube. And this is really how we get those two units that we just saw, the mmHg, millimeters of mercury, and the torr. We get this because on these barometers, there's usually like a ruler hanging out there, marked on the side, like a regular ruler. And a lot of times they're in inches, centimeters, and sometimes millimeters. So that's where that name comes from. Basically, you take the reading, and that's how many millimeters there are of mercury. So that's really where that name comes from. You'll also notice in this picture as well that mercury has a different sort of property in terms of its meniscus. Its meniscus actually goes the opposite way. It actually curves upwards. And you would usually read from the bottom of the meniscus. So here you would actually read up there at the top of the meniscus here, because it kind of goes backwards. So that's an unusual sort of property of mercury. Most liquids like water, for example, will have a meniscus that kind of curves downward like we've seen before. But here mercury actually curves upwards, really because the mercury is attracted to itself more than it's attracted to the glass. So instead of kind of going in on itself, it kind of goes up and over and makes that. The other unit of torr is also named because the guy who invented the barometer was a guy named Torricelli, and that's where that torr comes from, basically. So that's really where those two sort of units come from. One's more of a practical unit, like reading a ruler in millimeters of mercury, basically. And the other one's basically named after the guy who invented the barometer there. And that's where we get the torr unit, basically. Other ways that we can sort of measure pressure is through a manometer, and that's a device basically used to measure pressure of a gas. And there's two different sort of ways that this sometimes happens, and this is sort of an open system here. The top of it is open, which means the atmospheric pressure can kind of come in. It's not a closed vacuum type of deal. And basically, we can measure the height of the mercury here. So in this particular case, the pressure of the gas would be really the pressure of the height of the column here. And basically, you would measure, like with a ruler, how height it is from the below the gas to the top there of the mercury. And again, the atmospheric pressure in this particular case is pushing more than the gas pressure, because the gas is coming this way to push the mercury. The atmospheric pressure is coming this way to push it. And you can see the atmospheric pressure here is kind of winning, if you will, is pushing it much further down than we see on our opposite side here, where the opposite is true here. In this particular case, the gas is pushing greater than the atmospheric pressure. We can see the mercury actually coming further up the column here as well. And in this edition, what we get is the pressure of the gas is basically the atmospheric pressure plus the height of the column. In the previous one, we'd actually subtract it off because the atmospheric pressure is pushing harder on it. So again, this is another sort of common apparatus that is sometimes used to measure the pressure. You could also use an apparatus like this where the end of it is closed off. So basically this part here is closed, and basically you can measure directly the pressure as there's no atmospheric pressure sort of involved in that measurement by measuring the height of the column basically. So we're going to talk about some gas laws. And like I said, there's three sort of variables that we'll commonly see here. And again, that's basically pressure, volume, and temperature. And the first one we're going to look at is Boyle's law. And Boyle looked at pressure and volume, and he held temperature constant. So Boyle's law basically is looking at the relationship between the pressure of a gas and the volume of the gas while you hold basically the temperature constant. And what he saw here is sort of what we typically will see here is, excuse me, the pressure and the volume relationship is basically inverse to each other. So basically what Boyle saw was as the pressure went up, the volume went down, and vice versa. As the pressure went down, the volume went up. So that is basically Boyle's relationship here. And that's sort of what we see here. As the volume, a larger volume, a smaller pressure as measured here by the height of the column. A smaller volume, a much larger pressure here measured by the height difference of our mercury here in the tube. So it's just a logical sort of thought about it as well. If you just think about it, right? If we put some gas molecules into a volume such as this, say those three gas molecules, there's not a lot of room for them to move around, which means they're going to have a lot more collisions. A lot more collisions is going to cause a lot more pressure, as opposed to if we take those same sort of three gas molecules and then kind of put them into a much larger volume. They have a lot more room to move around, so it's going to take longer for these collisions basically to occur. Less collisions going to bring our pressure down. So it's kind of like giving everybody a lot more room to move around. Yeah, so it has a lot to do with the atmospheric pressure. So atmospheric pressure at sea level is 1 atmosphere. And when you go down, you have a lot more sort of pressure pushing on you, especially like, for example, if you go below water and stuff like that, there's just a lot more water pressure and all that as you go down, further down. And really it has a lot to do with like your lungs and stuff like that, right? So there's only a certain amount of space in there. So it feels the pressure, it starts to decrease the overall volume that you have, right? And obviously why you know, sometimes you wouldn't be able to breathe, obviously, if you went way too far down and stuff like that. Also why you get in trouble, right? If you go way too far down, say in the ocean, and then you come up really quick, right? So what you're doing is you're expanding, say, your lungs and stuff like that really quickly, right? As a change in pressure occurs just around you in sort of the atmosphere, and that causes sort of the problems. So we could also see this sort of relationship here on this chart. And again, the pressure here is 35.3 and the volume is, excuse me, 40. And coming down here, we see a much higher pressure when we basically cut the volume here. So again, a very smaller area, and it gets a lot less room for people to kind of fly around and move around, causing a lot more pressure. And that's what we see here on a graph. And this is a typical Boyle's law graph. And we can see again here at the smaller volume, a much larger pressure, larger volume, a much lower pressure basically happening. So there is a mathematical relationship, which is basically known as Boyle's law. And that is basically that P1 times V1 equals P2 times V2. So this is basically what's known as Boyle's law. And you do need to know this. And what we see up here is a relationship that we see that if you keep the temperature constant and you take a pressure point times a volume and you multiply them together, you will always get the same number. So you'll always get this constant number. And that's what the K here, this is basically this constant number. So if you did an experiment like the sort of table that we saw earlier there, and you took any sort of pressure times volume measurement and multiply them together, it will pretty much always come out to the same number. And that's basically how come we could kind of put this Boyle's law together. And this is sort of a before and after situation here. So P1, V1 is like before, then you change something, pressure or volume, and basically one of the other ones will change with it. Now, in terms of units, you're good in terms of units. It can be any unit, and volume here could really be any unit. The only deal is, like everything else, they need to be the same. So what I mean by that is whatever the pressure unit is here needs to be the same unit over there. And obviously here, volume, same deal, needs to be the same unit on both sides. So you don't necessarily have to have the pressure in any specific unit here. You don't have to have the volume in any specific unit, but they do need to be the same unit on both sides. And that's just sort of conversion wise. So everything will cancel out completely. And here we see a much better picture maybe than what I drew. But again, you can see here in the sort of larger volume, it really does give those gas molecules a lot more room to fly around. Again, going to cause less collisions causing our less pressure, as opposed to the far right there where we sort of squeeze the volume down into a very small area. Everybody's very crowded to each other. And again, we get a lot of more collisions basically occurring. All right. All right, so let's take a look at this one here. We have a sample of helium gas at 12.4 liters at 23 degrees Celsius and 0.956 atmospheres. What volume will it occupy at 1.2 atmospheres, assuming that the temperature stays constant? A very good thing, although we're only started with basically one gas law at this moment, a very good thing to sort of do here is just to pull out the information from the problem. And we see that we have a volume of 12.4 liters, and atmospheres is a pressure. So that's 0.956 atmospheres. We also have another pressure of 1.20 atmospheres, and we have a volume we're looking for. We actually do have a temperature here, but it does tell us that the temperature remains constant. So really, we're not even going to worry about that because basically it stays constant. We don't have to do anything with it. And why it's sometimes good to sort of write these things out like this is you could kind of almost hopefully see Boyle's law right there, kind of just from labeling everything. And I'll tell you, that's probably the best one to choose here. And in terms of numbering, usually people just go with how it is in the problem. So we'll call these guys ones. These guys will be twos. It really doesn't matter as long as you keep the numbers together. So in this case, we want to solve for V2. So when we want to go to the other side, we would divide by P2, right? So the pressures cancel. And that gives us P1 V1 over P2. And in this particular case, we would put stuff in. So we got our pressure of 0.956 atmospheres, our volume of 12.4 liters divided by our 1.20 atmospheres. Now, in terms of the pressure, we were all good because these units are the same, so they're going to cancel. In terms of the volume here, we did leave the volume in liters. And all that means is when we do solve for it, we will have liters as our answer in terms of units. And if we do that, that's going to be 0.956 times 12.4 and divided by 1.2 gives us something like 9.88. And again, because we left the first guy in liters, that will be the units that we see here. Any questions on that? And we also see here, in a good way to remember is, again, the sort of relationship. And as we talked about, as the pressure went up, the volume goes down and vice versa. So when you do your calculations, you can kind of see if it makes sense. So our pressure went up. We would expect our volume to go down, and it did here. So again, that basically makes sense based on what we know about Boyle's law. In terms of the answer, 3 sig figs, because everybody's pretty much got 3, and we're multiplying and dividing. So everybody here is 3 sig figs all the way around. Any questions on that calculation there? Okay. So why don't you try one here? So a gas sample with a volume 800 milliliters and 1 atmosphere goes to 250, what is the new pressure? So see what you come up with here. You do not. And we'll talk about STP a little bit later on this chapter. So you don't have to convert things to STP unless it tells you to. Okay, so let's take a look. So again, same sort of approach. You just kind of pull out the information. We have a volume that's 800 milliliters. We also have a pressure that's 1 atmosphere. Our volume then goes to 250 milliliters, and we are looking for a pressure. So again, you could hopefully see sort of Boyle's law in here. You could call the first guys ones, the second ones twos. And in this case, P1 V1 equals P2 V2. Again, in all these sort of gas laws, as we'll see, when we go across the equal sign, you basically, everybody ends up in the opposite location. So our V2 is on top. So basically it goes to the opposite location as you go across, basically. And if we solve for P2, that would be P1 V1 divided by V2 equals P2. We want to make sure that we put in everything that's correct in the right spot here. So we got 1 atmosphere times our 800 milliliters divided by our 250 milliliters, looks like. And in this particular case, again, both volumes were in milliliters, so we're okay. If they were not, you want to make sure you convert them. And if we do all that division there, it looks like we end up with 3.20 atmospheres. And that looks like it's D in this particular case. And we also see, again, our relationship, our volume went down in this case. So our volume went down, which means we would expect the pressure to go up. And it did go up from 1 to 3 atmospheres. So again, we do see our correct sort of correction there. And again, in terms of sig figs, 3 sig figs based off of the pressure that has 3 significant figures. Any questions on that particular one there? And there it is, just in case. There we go, one more time. All right, so the next sort of gas law we're going to talk about is what is known as Charles' law. And Charles' law, again, here looked at the relationship between volume and temperature, and they kept basically pressure constant here. And The relationship that we see with Charles' law is basically um, as the volume goes up, so does the temperature here. And as the volume goes down, so does the temperature as well. And that is because in a constant pressure, what's going to happen is, let's just say we have a gas at this sort of situation here. So if we increase the temperature, for example, increase the temperature, these gas molecules are going to pick up a lot more energy, which means they're going to start bouncing around a lot faster, right? They're going to start moving around a lot faster, which would cause a lot more collisions and cause the pressure to go up. So the way it's able to basically maintain the same pressure is as that temperature increases, so does the volume. And what that does is it gives everybody a lot more room to fly around when, even though they're moving a lot faster. And that's able to keep the pressure relatively constant. Now, the opposite happens if we decide, hey, let's drop the temperature. When we drop the temperature, the gas molecules are going to move a lot slower, and that's going to take longer for collisions to occur. And that means we would start to see the pressure come down. So in order to prevent the pressure from decreasing, what happens in terms of the volume is it decreases as well. By decreasing the volume, even though those gas molecules are basically moving slower, it's going to maintain the same number of collisions and be able to basically keep the pressure constant. Now, there's also another interesting sort of fact that happens when you look at a graph of volume versus temperature for a Charles law sort of relationship. And that's what we see here on this graph here. I think, there we go. And basically, if we look at a graph of volume versus temperature for any gas you like, and we'll get this sort of linear relationship. And if you take all of the lines basically and bring them all back to the temperature, they all hit the same spot, and they all hit in Celsius what is known as minus 273.15 degrees Celsius. And that number should look familiar to you because that is the number that we use to convert to Kelvin, right? Because temperature in Kelvin is basically temperature in Celsius plus 273. And if we add 273.15 to this, that gives us 0 Kelvin. And that's what we see here. 0 Kelvin used to be known as absolute zero. And basically what this means is pretty much every time you see a temperature in a gas law equation, it needs to be in Kelvin. So every time you see that temperature and any gas law, if you want to get the answer correct, you need to convert it to Kelvin. So again, a reminder to convert that to Kelvin, that's basically Celsius plus 273. And even in problems which sometimes trick people up is they give you the temperature in, say, Celsius, and then they ask you to give the answer in Celsius. You need to convert it to Kelvin, put it into the gas law, and then convert it back from Kelvin to Celsius. So that's a very common thing that sometimes happens. People mess up on that part of it. They're like, hey, they gave it to me in Celsius. They want the answer in Celsius. I could leave it in Celsius, and you will get the wrong answer. So definitely safe bet. Anything involving a gas law, you need to make sure that temperature is in Kelvin. And that does bring us to Charles' law relationship here. And this is V1 over T1 equals V2 over T2. Again, here, these are volumes kind of before and after. Volume in terms of unit, any unit you like, just like before, as long as they are the same on both sides. But temperature, as you can see here, does have to be in Kelvin for sure. So temperature does have to be in Kelvin. And again, that 273 relationship. Now, Charles' law looks at the relationship as we just talked about. And again, just like we saw with Boyle's law, in Charles' law, if you take the volume divided by the temperature, it will always come out to the same number. And that's what this basically means. And what we see with Charles' law is, like I said, volume and temperature holding pressure constant. There's also a gas law that's very similar to Charles' law, and it's what's known as Guy-Lussac's law. And that is P1 over T1 equals P2 over T2. And this is at constant volume. So this is at constant volume here. And in this relationship, what we see is as the pressure goes up, so does the temperature. And as the pressure goes down, so does the temperature. And that's because in this relationship here, basically the volume will not move. So a minute ago with Charles' law, we talked about the volume. It's adjusting to allow the pressure to remain constant. In a situation where your volume is rigid, it does not move. Basically what happens is because that volume doesn't move, if you increase the temperature, gas molecules will fly around faster, causing a lot more collisions and a lot more pressure, and vice versa. If you decrease the temperature and that volume doesn't move, your gas molecules is going to move around slower, and it's going to cause the pressure to start to decrease. So these are two gas laws which are sort of related to each other. One deals with pressure temperature relationship with his Guy Lusik's law, and one that deals with volume temperature relationship, which is basically Charles' law. And they're sort of ways that they change are similar. Volume increases, temperature increases, volume decreases, temperature decreases as well. So we have sort of that same relationship, sort of a direct relationship. As one goes up, the other goes up, and as one goes down, basically the other goes down as well. Any questions on those? So let's take a look at an example. So here we have a balloon that contains 1.3 liters, and we also have 24.7 degrees Celsius placed in a beaker containing nitrogen at minus 78.5 degrees Celsius. What is the volume at constant pressure? So again, here we have a few different gas laws to choose from. If we pull out the information, we have a volume that's 1.3 liters. We have a temperature that is 24.7 degrees Celsius. We have another temperature that's actually minus 78.5 degrees Celsius. And we are looking for a volume. So hopefully very quickly, you kind of see Charles' law here. We got two volumes, two temperatures. So this is definitely probably what we want to use is our V1 T1 equals V2 T2. Here we are solving for V2. And again, like I said, we're basically going to multiply to the other side, or the quick way of doing it is when you go across the equal sign, everybody ends up in the opposite location. So the T2 is on the bottom here. It ends up on top as you go across on the other side. So that's going to give you T2 V1 T1 equals V2. We do have to do some conversions here. Our temperatures are not in Kelvin, so we do need to convert those to Kelvin. So our T1 would be 24.7 plus 273, and that's going to give us 297.9 Kelvin. Our T2 is actually minus 78.5, so that minus is important, plus 273, and that's going to give us 194.7 Kelvin. At this point, again, we got their temperature in the right units. Also really important to make sure you get the T2 in the right location here. It's going up on top, so that's going to give us 194.7 Kelvin times our V1, which is 1.3 liters, divided by our T1, which is 297.9 Kelvin. Again, our Kelvins are going to cancel. And our volume is going to be in liters since that's the unit that's left over. And looks like we will end up with here. Looks like 0.8496. And again, here the unit would be liters. Looks like we have actually here what we got 3 sig figs. So we would probably round this here. So because we got 3 sig figs off of that number. So it looks like probably 0.8, and then that would round up to 50 liters would probably be our right answer there. Any questions on any part of that calculation there? Again, for a lot of people, the rearranging is the hardest part, and also the remembering to convert things to Kelvin, also sort of the hardest part there for a lot of people. So let's take a look at one here. Why don't you try one and see what you come up with? Oops, there you go. All right, so give this one a go. We got 1 liter of CO2 at 27 degrees, cooled to 15 degrees. What is the new volume at constant pressure here? Okay, so let's take a look. So again, kind of following the same approach here. I got a volume that's 1 liter. I got a temperature that's 27. We also have another temperature that's 15. And we are looking for another volume. Again, we do have an extra piece of information given to us, but we really could ignore it because it's constant. So really no need to even really worry about that one. It's just basically telling you that the pressure is not changing. So again, here we do see Charles' law, V1s and our V2 and T2. So in this particular case, we are looking for V2. So just like last time, we're going to bring our T2 to the other side. It will end up in the opposite location there. And just like last time as well, we do need to do some conversions here. So we got 27. So we need to add 273 to it. And that gives us 300 Kelvin. For our T2, we also need to add 273 to it to convert it to Kelvin. Always need to convert it to Kelvin, no matter what. And now we got everything that we need. So taking our T2, which is 288, times our V1, which is 1, divided by our T1, which is 300 Kelvin. Again, here the Kelvins will cancel, going to leave us with liters. And if we do that there, looks like 0.96 liters in this particular case. Any question on that there? We also see the trend that we talked about. Again, our temperature went down. So when our temperature goes down, we would expect the volume to go down as well. That's how it's able to maintain constant pressure. And it went from 1 liter to 0.96 liters. And the same deal on this one, the one that we saw previously in terms of our relationship. Our temperature here went down, and then our volume obviously went down as well from 1.3 to 0.85 in that first one. Any questions on Charles' law, Guy-Lussac's law? Again, the key problem people have on these is that converting to Kelvin, and again, the rearranging of these sort of formulas. So again, if that's a problem for you, you want to make sure you take some time to figure out how to properly rearrange these formulas so that you do end up with the correct sort of answer at the end there. Any questions on any of that there? So adding to our list of gas laws is one where we actually can look at all three variables together. And that is what is sometimes referred to as the combined gas law. So the combined gas law pretty much deals with everybody together. So that's P1 times V1 over T1 equals P2 times V2 over T2. Again here, just like before, these guys up on top can be any unit, your pressure and volume. As long as, like everything else, they're the same on both sides. So they do need to be the same on both sides. Temperature, just like any other gas law, needs to be in Kelvin. Yeah, so these guys, again, need to be in Kelvin. Pressure could be any unit you like. And again, our volume could be any unit you like as long as they are the same on those of those. So why don't we try one here and see what you come up with. So give this one a go. We'll talk about it here. Just make sure. Got somebody at 25 degrees Celsius, 0.756 atmospheres, and 0.5 liters. We want to know what is the pressure if we kind of change the temperature and also change the volume here. Okay, so let's take a look. So if we kind of just pull out the information like we've been doing, and I start scribbling all over the page here, we have a temperature that's 25 degrees Celsius. We also have a pressure that is 0.756 atmospheres and a volume that is zero point 0.5 liters. We're looking for a pressure, and we have another temperature of 55 degrees Celsius and a volume of 0.65 liters. So again, hopefully by just doing that, you should see that the combined gas law that we were just looking at is probably the best one to use, as it deals with all three variables together. So that is our P1 V1 over T1 equals P2 V2 over T2. Again, we're really looking for, if we call all these guys ones, all these guys twos, we're looking for P2, which means in this case, we need to move V2 and T2 to the other side. And again, you could do it multiplying and dividing, or again, just a quick way is T2 is going to go to the top and V2 will go to the opposite location and go to the bottom, and you'll get there really quickly. And that would give you something like T2 P1 V1 divided by V2 T1 equals P2 when you do that. In terms of units, our volumes are okay. They're both in liters. Our temperatures, like normal, are not okay. So we do need to convert those into Kelvin. So our T1, if we add 273 to it, should give us 298 Kelvin. And our T2, if we add 273 to it, should give us 328 Kelvin. Now we got pretty much everybody in the right units. The key again here is to make sure we get everybody in the right side, up, down, and all the right numbers there. So our T2, which is 328, goes up on top. Our P1, which is 0.756, goes up on top. And our V1, which is 0.5 liters, should go up on top. Our V2, which is 0.65 liters on the bottom. And lastly, our T1, which is 298 on the bottom. Kelvin going to cancel, liters going to cancel, going to leave us with atmospheres, which is good because that is what we're looking for. And looks like we will end up with an answer. That probably has numbers. Let's see. And it looks like we end up with 0.640, it looks like, perhaps. And again, the unit here would be atmospheres there, if I did that right there. Any questions on that one? So the combined gas law, really one that gives people a pretty difficult time sometimes. And again, it's the rearranging part here. So if it's easier, just remember opposite as you go across that equal sign, and just a quick way to quickly rearrange that really quick. No, it doesn't. It doesn't necessarily matter in terms of that. You can just plug it in and do it. It's basically the same thing as rearranging it. You don't necessarily have to show it rearranged, but you do need to show some type of work, I guess. You can't just have a number. So you got to show some type of work. If it's just basically our original guy here where you popped in the numbers and then solved it, that's probably okay in that case, if that's your question. Other questions on that? Okay. So that is our combined gas law to add to our ever-growing list of gas laws. Then we want to add some more, because why not? So let's take a look at some more gas laws here. And our next one comes from our good friend Avogadro. He had a number, but he wanted a gas law as well. So when we think about Avogadro, right, we think about number of moles equals Avogadro's number. So it would make sense that his gas law involves moles. And with Avogadro's law, that is when we have conditions of pressure and temperature are constant. So at constant pressure and temperature, we do get this sort of Avogadro's law, which is V1 over N1. And N is the number of moles of the gas. So these are number of moles, which makes sense, again, based on Avogadro's number. So V1 over N1 equals V2 over N2. And here, the volume, again, can be any unit you want as long as they are the same. And N will be moles, obviously, in this case. So these got to be moles, obviously. And really, the relationship that we see with sort of Avogadro's law is basically as the moles increase, so does the volume under these conditions. And almost as we will talk about maybe later on this chapter, for example, if we looked at an equation like our H2 plus N2 gives us NH3. And when we do something with stoichiometry, for example, we would say, right, that there's like 3 moles of H2 gives us 1 mole of N2. We could also say for 3 moles of H2 gives us 2 moles of NH3. We could say 1 mole of N2 gives us our 2 moles of NH3. So we could do a mole-to-mole relationship like we talked about in stoichiometry, but if this was at constant pressure and temperature, we could actually do a volume to volume relationship, very much like stoichiometry. And we could say for every 3 liters of H2, we would need to put in there 1 liter of N2. And it's basically kind of the same thing as that mole to mole relationship, because under these conditions, basically the moles and the volume will basically be the same. They change the same way. You could also say, for example, just like that, for every 3 liters of H2, you get out 2 liters of NH3. 1 liter of N2 would give you 3 liters of NH3. So as we'll see maybe a little bit later on, sometimes this might help with some stoichiometry problems, especially if you're under conditions of constant pressure and temperature. You can basically, the moles and the volume are almost equivalent to each other. So as the volume changes, the moles change pretty much equally to it. And we could kind of get almost like a mole to mole relationship, or really a volume to volume relationship that occurs in a sort of reaction that is at those conditions. And we'll talk a little bit more about that probably later towards the end of this chapter. So let's take a look at this one here. We have 2.45 moles of argon. So we do have moles, which is 2.45. And we have a volume that's 89 liters. And we want to know what is the volume if the moles go to 2.1. So again, we have volume and moles, which gives us the Avogadro's number. Again, basically same conditions of pressure and temperature. That's a fancy way of saying temperature and pressure are constant. Right. So we have our V1 over N1 equals V2 over N2. In this particular case, we would solve for V2. So this guy is just going to go up there to the top. So that's going to give us N2 V1 over N1 equals V2. In this particular case, we're good to go. We got moles on everybody, and that means our volume will be in liters when we solve for it. So N2 would be 2.1. V1 will be, that was 89, right? Yeah, 89, there we go, 89 liters. And our N1 was 2.45 moles. Again, our moles are going to cancel here. And that's going to leave us our liters. And we will end up with, looks like 76.3 liters. And we sort of see the relationship. Basically, the moles went down, so did the volume there. So it kind of changed the same in that relationship. So this is really a more sort of direct application of Avogadro's law, where you basically just plug and chug in there. Again, you could also relate it to stoichiometry like we talked about there a minute ago. Any questions on that one there? All right, so why don't you give one a try, which I think is the next one you got. And 3 sig figs on that last one based on how many we had on the problem. So see what you come up with, A, B, C, or D here. All right, so here we got moles, that is 1.32. We also have a volume that is 2.3 liters. And we're looking for volume again, I believe. And we have moles, that is 4.56 moles. And in this particular case, again, we could hopefully see Avogadro's law happening. So V1 N1 equals V2 N2. In this case, again, we're going to move our N2 to the top, and that'll give us N2 V1 N1 equals V2. Everybody's in okay units here, so we'll go with N2, which is 4.56 moles, times our V1, which is 2.3 liters, divided by our N1, which is 1.32 moles. Moles will cancel, going to leave us liters when it's all said and done. So 4.56 times 2.3 divided by 132 gives us something like 7.9 liters. Looks like B here. And that's because sig fig wise, this guy's got 3, this one's got 2, this one's got 3. So we should end up with 2 sig figs when it's all said and done here, based off of our liters there. Question on that calculation or Avogadro's law? So far we've seen a number of different laws. We've seen Boyle's law, Charles' law, Guy-Lussac's law, combined gas law. We've now seen Avogadro's law. And if we pretty much put everybody together there, take all these gas laws and really put them together, we do get the granddaddy of them all there, and that is going to be our ideal gas law. And our ideal gas law is PV equals nRT. And this is what is referred to as our ideal gas law. And this gas law here is obviously very different than a number of the other gas laws. First off, it is different because there is no before and after type deal. So we only have one pressure, one volume, one temperature, no two of everything. The other thing that makes it really different is units. And the units are really restricted. When you use the ideal gas law, the pressure has to be in units of atmosphere. When you use the ideal gas law, the volume has to be in liters. The N should hopefully be in moles, and the T has to be in Kelvin. And the reason all these guys have to be in those units is because of R. R is our gas constant, and it has a value of 0.08206. Some people round it 0.0821, but I use this number. A lot of people will use this number, but a good amount will still use the rounded number as well. And that's because it has all 4 of those units. So the good news is, if you don't remember what the units everybody needs to be in this equation, you could look at the gas units here, the gas law, constant units, and it tells you pretty much everybody's units that they need to be in. And that's for everything basically to cancel out correctly. So an ideal gas is basically a gas which behaves ideally. That makes sense, I suppose. But basically what it means is, as we'll talk about, is it pretty much is unaffected by other gases. So under normal conditions, even if you have multiple gases kind of flying around in there, it's sort of unaffected in terms of their interactions or anything like that. We think about ideal gases as, even though there's multiples in one location, that they're kind of there by themselves. And that's sort of what an ideal gas sort of is. And we have PV equals nRT. Again, pressures are P, or V is our volume, N is our moles, R is our gas constant, T. This is a constant R, so you always have this number given to you, no matter what the situation is. You always have that available to you. So let's take a look at one here. An automobile tire at 23 degrees Celsius has an internal volume of 25 and a pressure of 3.1. Determine the number of moles of air. So if we do our same approach here, we have our temperature that is 23 degrees Celsius. We have a volume that's 25 liters. We also have a pressure that is 3.18 atmospheres. And we're looking for N. So you can almost pretty much see the ideal gas law there just from writing out everything that's present. So PV equals nRT. And we can even check off what we have. We have pressure, we have volume, we are looking for moles, we have temperature, and not usually given to you, but again, since R is a constant, you always have that number 0.08206 liters atmosphere Kelvin mole. That means we can basically solve for N. Same idea to solve for N. We're going to divide RT to the other side. Those guys will cancel each other out. And that will give us PV over RT is equal to N. In terms of units, our volumes in liters, so it's good to go. Our pressures and atmospheres, if I wrote it, it's good to go. But usually our temperature here is not so good. So we do need to convert our temperature. So we are going to want to add 273 to that, and that will give us 296 Kelvin. Now we're good to go in terms of units. So we could put them in. We got a pressure of 3.18 atmospheres. We have a volume of 25 liters divided by our R, which is again a constant. You always have this number. And lastly, here we have our temperature, which is 296 Kelvin. In terms of units, liters cancel, atmospheres cancel, Kelvin cancel. We are left with moles, which comes up on top when you divide it. And it looks like we do end up with about 3.27 moles. And you can take your pick of any of these guys that have 3 sig figs as to why you should end up there in terms of the answer. Any questions on that particular one there? So again, the important part is you want to make sure definitely with the ideal gas law, everybody's in the right unit. Super common mistake that people make is, again, not converting things to the proper units before they go into it. Any questions on that one? All right, so why don't you give the next one a go and see what you come up with. By the way, helium is 4.003 grams per mole. Okay, so let's take a look since we're getting to the end here. We're looking for a pressure. We do have a volume that's 304 liters. Contains, we actually have a mass of 5.67 kilograms of helium. And we also have a temperature here of 25 degrees Celsius. So again, we pretty much have one of everything. We do have mass, and from mass, we can get to moles. So really, we do have P, V, N, and T, and we always have R. So again, this is going to be our PV equals nRT. We do have some conversions to do here. Our volume's okay. Our temperature, we do need to convert to Kelvin, so we're going to add 273 to that. Going to give us 298. Now our kilograms here, we need to get to moles, so we're going to need to do 5.6. Again, 5.670 kilograms. In 1 kilogram, there is 1,000 grams. And using the molar mass from the periodic table, there's 4.003 grams per mole of helium. Again, the kilograms will cancel, gets us to grams, which then gets us to moles using the molar mass there. Looks like maybe something like 14, 16 moles of helium in this case. So we now have our volume, we now have our moles. Remember, we always have R. And we do have our temperature. So to solve for pressure, that would be nRT divided by V, bringing V to the other side here. And put in our numbers in, gives us 1416 moles. Our R, which is 0.08206. Our temperature, which is 298, all divided by our volume there, which is 304 liters. Moles will cancel, Kelvin will cancel, liters will cancel. That's going to leave us atmospheres as the only unit left, which is good because we're looking for a pressure. And we will end up with, looks like 100 and, guess we'll go with probably like 114 on the rounding there, 114 atmospheres, again, based off of this number here, which is 3 sig figs. Any questions on that particular calculation? A very common thing that you sometimes have to do with ideal gas laws is take something from grams and convert them to moles using the molar mass like we've done before. Any questions on that one? Okay, so we'll stop lecture here. We will continue talking about this, I think, in lab, as our labs this week is about gases. So we'll probably continue on talking in this lecture here, and then we'll get into the labs that's going on this week. All right, I'll see everybody in about 10, 15 minutes, and make sure you put here if you haven't done so.